recording now. So last week we left you with a cliffhanger at the end. We had given you both propositional equality and then showed you what it means to satisfy Leibniz law, which is to say that two values are equal whenever you cannot distinguish them by any property whatsoever. And then what I said is that, well, all of the functions we implemented by pattern matching, symmetry, transitivity, and so on, you can actually all reduce them to substitutivity, or Leibniz law, whatever you want to call it. So, of course, in the standard library, we use something else. So you can chase down the definitions. And we're saying that a relation is substitutive whenever, for any property, okay.
Yes.
If we have P, what?
Yeah.
P, what? Oh no, P implies P respects. Is that what?
No, it's extremely confusing syntax. That's what's going on. Someone's taking the mickey. Arrow respects is all one thing, and it breaks down.
Oh, and it's feeding like P in both places. Okay, yeah, that's it.
Yeah.
So that's the real definition. Whenever X is related to Y, then P of X implies P of Y in this instance. Okay, that was not the best. Let's look at week 2. So substitutivity, we had it at the bottom.
Yeah.
We're saying this. So instead of chasing the definitions, this is what we had. And modulo the order of the arguments, it's the same thing in the standard library. So if you remember last week, we reorganized the definition so that we would take the property last, because this way we're saying this equality in terms of that one. But in the standard library, we take the property first. So, I mean, that's the only thing to know. Right, so how do we prove symmetry of equality? So we have a proof that X is equal to Y, and we want to prove that Y is equal to X. And we have substitution telling us that whenever you see Y, you can just have X if you want, as long as you're able to prove that they are equal to each other. So the whole point is to look at the goal that you want to discharge, and then make that predicate be exactly the goal that you want to discharge. So here, let's see if I can do that. I'm going to say, for whatever Y is, okay, so I need to name X then. I need to have a name for X because X shows up in the type. So when I'm going to build my predicate, I'm going to mention it X at some point. So I need to have a handle on it. So I'm saying if X is equal to Y, then Y is equal to X.
You're going to need the, well, yeah, okay, you can play it that way if you want.
And then I have a lot of unsolved things. So here I have exactly what I wanted, but now I have abstracted over Y. So the Y is gone, and it could be anything I want. This meta variable here saying, I don't know yet what it is. It could be anything. And if I want to be sneaky, I can just say, I want just the trivial proof, basically. So if we roll it back, right, what does it mean for the implicit arguments? I'm going to take this proof and return it immediately, meaning that this X is going to become the solution for that meta variable. And this X is going to become the solution for that meta variable. Both meta variables are the same, but the solution is X in both cases, so it's fine. So this is a function of type X equals X goes to X equals X, which is not super interesting, but up. And then here, oh, did I screw myself over?
Yeah, you did. You're doing it.
I'm doing it backwards.
Yeah, and you're doing it a more complicated way than you need, I think.
Okay. So let's do second attempt.
Yeah.
All right, so let's get rid of this stuff. Okay.
Ah, right. You're using subs in the library way. Okay, fine.
Yeah.
Um,
Okay, so second attempt. So before, I was just not doing anything with the proofs, and then the constraint was that I needed to prove again that x is equal to y, which is not super helpful, especially because I didn't introduce it. So now I've introduced the proof that x is equal to y, and I need to prove this. So,
so the message is, when you're looking at the goal, right, you've got this equation, x equals y. Subst tells you that if your goal talks about y, you can make it talk about x instead.
yeah.
So what you do is you deliberately capture the y in the goal by writing lambda y, right? You choose, although it's not supposed to be important here, conceptually that's the move. You say lambda y and then you copy the goal. And that says, this is the y that I'm going to turn into an x. And yeah, we sure would prefer.
And so you can even do this, right? You don't need to abstract over all of the occurrences of y. Here, there's only one, so it doesn't matter. But in practice, you could say, I'm going to target some of them. And then where you say target, it's the ones that you've abstracted over. And when you say y, it's the ones that you've kept around. Okay, so there's this. Then I need to prove that something is equal to y, and that something is what will be, what y will be replaced with. And handily, I have this proof in context. And now the result, well, the result is that predicate applied to x now, instead of being applied to y. And so now I need to prove that x is equal to itself, which is easy with REFL. Okay. And here we're going to play a similar game. So I'm introducing the names. I think, let's see. So we know that x is equal to y, and we want to turn y equals to z into x equals to z. So you can see that if only x were the same as y, we could have the identity function here, because then we would transport the functions across. Yeah. So that's exactly what we're going to do then.
There are two ways to skin this cat, and this is a good one. Yeah, so the important thing here is, if you want to use x equals y, right, that gives you the superpower to turn y into x. You need to keep this y in the goal, because that's the thing. We've just turned y into this target here. If you'd skipped past that, then there'd be nothing in the goal to grab onto. However, there's an alternative proof.
Oh yeah.
But
well,
do this one. If you do this one, then we can look at the other one, I suppose.
Yeah. So then again, I need to pick what y should be turned into, and I just have x equals to y, so I might as well use it. And now I have this
identity function.
Identity function.
Right.
Do you want to do the alternative definition?
Yeah, why not? Okay. It's, you know, I like to prove trans. Okay, let's see what I have to name. I will do this thing. So this is a kind of standard Agda programmer move, is to choose variable names that look like the proposition their proofs solve by squeezing all the spaces out. Okay, so here I've just what happened?
You need to reload.
Oh. Right, here I've just, on autopilot, I've named all the inputs. And now I'm looking at the goal, x equals z, but I know two equations. And I need to have a little bit of a think, because I've got two equations, which means I've got to make a decision. You know, which of these equations is any good to me, right? So remember, subst lets you take the right-hand side of an equation and turn it into the left. So I have two superpowers available. I can turn y into x, or I can turn z into y. And given that the goal doesn't talk about y, it's pretty obvious which of these superpowers I ought to use, right? There's no y to turn into x. There is a z I can turn into y. So I will say subst, and the predicate I will give is going to be something is equal to, I'm just going to do this operator section thing. And then I say refine. And that wants to be y is equal to z. And now my goal, wonderfully, if I normalize it, is, well, I'm hoping I can get away with sticking x equals y in there. I can.
Yes.
So that's slightly more first order. We're not transporting a function. We're just returning this proof into that proof. But it's the same thing, really.
Yeah.
But
So more generally, we can prove that propositional equality and Leibniz equality are equivalent. And how do you do that? Well, first, you introduce a name for Leibniz equality. So if I remember correctly, I named it something like this. And whatever.
Oof, I'll never be able to type that.
And then we can say to Leibniz, which should be easy.
Well, you need to, have you defined Leibniz yet?
Oh no, that's a good point. I've just named it. What is it? It's taking a set implicitly and then an x and a y of that type and returning another set.
Is it going to be a set though?
I don't think it needs to be more general. Does it need to be more general than that? Oh yeah, okay, I see what you mean. A p of x implies p of y. Yes, I need to have that name in scope.
All
right.
I saw that coming.
Yeah, so
Yes.
What's going on here? I'm saying that this is a set, but then I'm defining it by ranging over all families of sets. And if this is a set, it's also part of the it's a trivial family of sets where the answer is always doesn't depend on the first value. Meaning that we're sort of defining it in terms of itself, right? And that would lead to a paradox. So this is the classical.
Yes. I don't know if you've encountered like paradoxes like things like the set of all sets which don't contain themselves. Russell's paradox, things like that. So Russell escaped from his own paradox by inventing this idea of a hierarchy of levels of sets. And the bottom hierarchy is boring ordinary sets that definitely don't talk about sets. So if you have a set that talks about sets, it has to go further up in the hierarchy. And look, here's us talking about sets. So that thing which talks about sets is not allowed to be a set. And that's how we get out of the nightmare.
Yeah, and so Agda sees this thing, which is large, and so gives it a large type, so set 1, which is just above set, which stands for set 0. And then it's saying, well, that doesn't fit in there, so you're not allowed to have it. We can actually make it even more general, right? So, what?
Oh, go on.
That'll be fine.
Yeah.
So something you'll maybe see if you explore the standard library a little bit, or maybe even in the project, I can't remember whether I'm using large things or not, is that these constructions, a lot of them, even though they might be increasing the size of the sets you're considering, they're sort of uniform. And so instead of defining Leibniz equality for sets and then Leibniz equality for set 1 and Leibniz equality for set 2, etc., you can just say, well, whatever the level is, if I have a set L here, I can define Leibniz equality for it by just growing a little bit. And so the definition will be one level up, but it's valid across all possible levels. And so here I'm going to say, well, now I need to introduce the level also. Oops, no, oops. And then I'm saying for any predicate at level L, X should be indistinguishable from Y.
So yeah, that's the general situation is that if you talk about sets at one level, you live at the next level up.
So what is 2 Leibniz saying? Well, it's saying that if I have a proof, like an inductive proof of equality, a piece of data I can get my hands on, then I can get a proof of Leibniz definition of equality. And this,
If I remember rightly, Leibniz doesn't have a T, but
maybe in French.
yes.
All right, and okay, seen like this, it's maybe a bit puzzling, but if we normalize it, if I can get, where is it not normalizing it? There we go. Ooh, okay, that's disgusting. But anyway, what we're seeing is that we have equality, and then for any predicate, px implies py. This is exactly what subs is giving us, right? So modulo the order of arguments. So I'm grabbing the equality, and then I'm calling subst. I guess I need to grab the p also, because they're in a different order. Well, okay, and going the other way, well, as you might expect, we've seen already how to do it with symmetry and transitivity. It's all in picking the right predicate to have. So here we're saying for any predicates, if I have p of x, I have p of y. And in particular, I want to prove that x is equal to y. What predicate do I pick? Well, I'm picking the predicate saying x is equal to something. And then I can prove x is equal to y by proving that x is equal to x. So that's x equals Leibniz y, which I'm going to copy paste. Y, well, I guess I can use the section like you did. Maybe it's, and then I'm left with the goal, x is equal to x, which I can prove using the inductive notion of equality now. So whenever you have an equality, however you came to it, you can just turn it into the other kind of equality, basically. Okay. So what we're seeing is that the notion of equality, which is a notion of proof, is also the same as sort of a function that takes a predicate and then transports values along it. And this is actually a deep observation in type theory. We can draw a correspondence between various things that are on the computing side, on the data types, data structures, and also on the proving side, on the building arguments in favor of a position. So the thing I wanted to do first, we've already seen a little bit of this when we're looking at proofs of equality, and we said, okay, it's possible to prove that 1 plus n is n plus 1. We do this by induction over n, etc. But it was not possible to prove 17 is 42, which is reassuring for any notion of proof, right? So this was wrong. If you remember, you just get a type error. But then we're able to prove this thing. Oops. Yes.
Yeah.
And now we are going to see how it's actually encoded.
So remember, there are two ways to write a function in Agda. There's the usual way, which is to name the input and say what the output is, and then there's the go away method, where you point out why the input can't ever exist. So, like, we're saying, dear Agda, you check that there's no way an input will ever turn up. And Agda actually peels the successors off 17 and 42 until it gets down to 0 is whatever it is.
Yes.
25.
Right, so how is this encoded? Well, we sort of told you 2 weeks ago that basically what we're doing is we're assuming 17 is 42, we're going to return a proof of the empty type, which is a way to say that it's absurd. But we can actually define this, right? So we can say the empty type is a set that's defined by induction, and we just don't give you any constructors. And so once you have this, there is no way for you to build a value in the empty type, which is reassuring because it should be empty. But there is a way to prove that if someone claims to have built a value in the empty type, you get to call them out and do anything you want with it. So in particular, you can do this. It's called the principle of explosion, saying that if you give me a proof of the empty type, I can build anything I want. And this is exactly proven by the same thing, because you tell Agda, well, clearly there's no way this could be built. It looks at the definition, there are indeed no constructors, there's no way to come to it, so you can just do whatever you want. You can dismiss that branch entirely. That branch is just impossible. Yes. So that's the, right, so we saw here 17 equals 42, appealing to Agda's magic, telling it, well, just check that this is true. But maybe this is not entirely convincing for you, and we can actually show you a proof, a more direct proof of this. So how are we going to do this? So we have our proof that 0 is equal to 1, and then we want to build the value of the empty type. And we're saying we are not allowed to match on this, because if we match on this, it's exactly the same as the anonymous lambda we gave you before, right? You just guess this empty pattern saying, yeah, I know it's impossible. So the only other thing we know about equality is that two things that are equal behave the same, meaning that if you have a proof of something for one of the values, then you can have a proof of the same predicate at the other value. So the trick then is to pick a good predicate that will allow you to move between empty and something that's actually provable. So let's do it like this. I'm going to define my predicate in a separate, in an auxiliary definition. And here I want to say that subst of P applied to 0 equal to 1 is something that's easy to prove. Okay, I'm not getting yellow, that's strange.
It is strange.
So what I'm seeing now is that I need to be able to prove P0, and I have a constraint. Okay, that's not really helpful.
Yeah.
Is that the only constraint? Yeah, it's the only constraint, okay. But P0 should be provable, so I'm going to split on...
Oh, finally we're getting that. We need to know that this goal 0, when n is 1, has to give us the empty type.
Oh, yeah, okay.
Right. So remember that we know, allegedly, 0 equals 1. So we have the magic power to turn a 1 in the goal into a 0. So we would like P of 1 to be the empty type.
Yes, so this will transport a proof of P of 0 into a proof of P of 1. So for the types to match up, P of 1 needs to be the empty type. And here we're just going to say P of any successor thingy is the empty type.
All right. And then we need...
And then here we need to be able to prove P of 0. Why is it not telling? Oh, because
right,
it's been
because
introduced
exactly,
here now.
it's got as
Yeah,
far
okay.
as computing that whatever
Yeah.
that whatever we put here is going to be the type of that thing. So all we have to do is think of something that's easy.
And I mean, we have
That'll do nicely. Can we
natural
think of a
numbers,
number?
for instance, and so we can just put in a number. And this might seem just like absurd, right? But as we said, because the argument to this function will never be built unless you're already in some absurd context where you can prove anything you want using the explosion principle, it's safe to just do some symbol mangling like this and just say, yeah, I can turn a natural number into a proof of false and so on. It doesn't matter. We're just convincing Agda that this branch will never be explored.
Yeah, but also just look at it from this perspective. What we're saying is we can write a program which tells 0 and 1 apart. Therefore, they can't be equal. You know, if they were, if Leibniz says if they were equal, we wouldn't be able to tell them apart. And we can tell them apart.
And this becomes handy when we have things that are more complicated than just a piece of inductive data that's claimed to be equal to another piece of inductive data, both of them closed, etc. So for instance, if we're trying to prove that plus and times are not equal, well, if you try to do it like that, it's going to be a bit tricky because, I mean, this is just a function definition that's defined by pattern matching, and the same for times. And it's actually really hard to decide whether they are equal, whether they will send all equal values to equal outputs.
So expectation management, you can expect Agda to be able to tell the constructors, different constructors of the same data type apart. Right? It knows, it can tell 0 apart from 1. But it's too stupid to do any other equational reasoning. So we're going to have to think of something clever. And in particular, we're going to have to think of a property of addition. We've got to have some property that enables us to tell plus apart from times.
Yeah, so the only thing you can do with these functions, you cannot pattern match on them, you cannot inspect their code, whatever. The only thing you can do is feed arguments to them. So the trick then is to find two sets of arguments so that, well, the same set of two arguments, so that if you feed them to the left and if you feed them to the right, you will get different answers. And therefore, it's not true that the two functions were equal, because if they were equal, then we need to send equal arguments to equal outputs. And I've set it up just the wrong way. Luckily,
yes, you did.
luckily, I have symmetry, so it doesn't matter. So as Connor said, you could just pick, you could go back to substitution, pick a predicate, etc. But we already have a proof that 0 is not equal to 1, so let's reuse that. Then flip it around.
Yes.
And then I'm going to sneakily add one import, Kong2. Oh. Or no, is it Kong?
I don't know.
Oh no, it's the wrong one.
Further up.
Oh, it is imported already.
You've got Kong, but
yeah, so what am I going to do? Well, on both sides I have a function, so I can apply congruence, use my function, and then modify it on the
So we're going to feed two numbers in. Which number should we pick?
we want to get 1 on
we
the
want to
left-hand side using plus.
We want to make times output 0,
And
and we want to
0.
make plus output 1. So if we feed in, if you feed in 2 zeros, then it's not going to be good enough. But nearly. we want plus to live and times to die. Well, we've already killed times. Right. So, right. So, yeah, if we feed in 0 and 1, then plus will give 1 and times will give 0. Then 0 isn't 1, so we're laughing.
All right. So then we saw 2 weeks back that we defined negation here somehow. And from what we've seen just now, you can see that negation as a generic principle is just, oops. If you give me a proof of A, then I can demonstrate I can get a proof of bottom.
And from there, anything.
Yeah.
So,
and so we're starting to stack things. We can prove that it's not the case that the empty type is inhabited. Which is a bit of the most
if we had an element of the empty type, we could make an element of the empty type.
Yeah, once you start unfolding the definitions, it becomes pretty self-evident. So the identity function is also proof that the empty type is not inhabited. Do you want to do double negation introduction?
All right. Okay, so we want to say, if we've actually, honest to goodness, got a proof of A, then we are going to be able to show that A is not impossible. I mean, we've got one. I mean, this is like saying, I've got one in my hand. Look, they exist, you know. Right, okay. So it's like, what's happening here? If I normalize the goal, you can see that somebody is telling me that there is no evidence of wrongdoing in the Epstein files. And, okay. If I normalize everything, you'll see that that NA says there's no evidence of wrongdoing in the Epstein files, except that A is the Epstein files. So they're lying. Okay. But then here's...
yeah, another way to see it is that you reached a contradiction, right? So sometimes you can invoke also, you could name this contradiction, for instance, because whenever you have a proof of A and the negation of A, then you can conclude anything you want.
But yes. Once upon a time, the timetable arranged for me to teach first-year hardware like truth tables and double negation elimination, as works perfectly well with Boolean circuitry, and then to rush to a lecture on advanced functional programming, in which I would have to say, oh, that thing I told you 3 years ago, turns out it's bullshit. So yes. These days, I don't actually wait till fourth year. So here, let's look at what we've got. Somebody is telling us you can't disprove that there are fairies at the bottom of the garden that disappear when you look for them. And we are being asked for the fairies. But, you know, when we look for them. Right. So what we're saying here is that, you know, just because you can't prove it's impossible doesn't mean you know how to build it. So we can, I mean, it's also the case that, you know, we can't inspect what X is. We don't allow programs to actually introspect on types. And if you think about it, if this was going to work, right, it would have to think a little bit, what is this type X? Is it one of the possible ones, in which case we definitely have to be able to build one? Or is it one of the impossible ones, in which case we have to refute not X? If there was something like this which worked the same way for all X, we would be in serious trouble. So thank goodness we can't write this program.
Yeah, in particular, if you think about X being the empty type itself, right? There's no way you're going to prove it directly. So the only way is to call this function, as Connor was saying, like refute whatever argument you're passed. And then you have to build an identity function here, but that's fine. We know how to do that. So sometimes we do build, we need to sometimes build the value and sometimes just not.
Yeah. So the most we can hope for is if you know the law of the excluded middle for a given type, right? If you know this thing is either true or false, then you can extract.
Can we not prove something like this? Like, no, no.
Yeah, okay, you should actually be able to do, never mind that, just add an extra layer of knots.
Oh, the 3 knots into, yeah.
Yes. Yeah.
Any prime. No, X. Well, the difference here, of course, is that now our target is not X, meaning that we're going to get our hands on one X.
Yes.
So we get to know that X is inhabited. So we get an X here. And then we can see that here, if only we could just double negate X, then we could get a proof of the empty type. So we can use that not X on the goal. And now we need to prove not X from X, but we've just seen above with double negation introduction that you can always like lose information in a sense, right? Because you're starting from a concrete proof of A, and you ended up ending up with a proof that it's not the case that A does not hold. So it's weaker in a sense. You can always weaken your assumption and get this thing. And at some point, so the knots just stop mattering. So when you have 3 of them, it's the same as having just 1. When you have 4, it's the same as having 2, etc., etc.
Yeah. High-level message. Double negation elimination doesn't work for things which are positively bit-bearing, right? You can't use it to make actual stuff. But it does work for negative things, right? So refutations, proofs of not something, they don't enable you to build things. They enable you to tell people to go away. And sticking an extra not round something negative doesn't make the blindest bit of difference. You can put it in, you can take it away, because you weren't ever going to build anything anyway. There were no bits were harmed in the making of this function. Right. What we're saying is that you can't magic up actual bits of data from negative information. You know, they've got to come from somewhere.
And you might think that it's extremely useless to talk about all of these impossible cases, but the whole point is that once you start implementing your data structures with a lot of invariance internally, it's actually really useful to be able to say all of these branches are dead, I don't need to write any code for them, and I actually have a proof that they will never be reached, as opposed to just leaving the cases out, and then, oops, you made a mistake in the invariance, and now suddenly that branch is taken, everything crashes. So it is useful to be able to tell people to go away. All right, implication. We've already seen implication a little bit because we kept telling you that when we have the negation of something, it's another way to say that from that thing, we could prove that we have a value of the empty type. And so implies is just a more general version of that. So what does it mean to have a proof that A implies B? So here we are saying that triple negation implies single negation. It's just having a proof that from, if you give me a value of type A, I can give you a value of type B.
Yeah.
So just a function.
That's the idea. If you think of types as sets of proofs, so what we're saying is, if you give me a proof of A, I will give you a proof of B. One thing that you have to be a little bit careful about as far as this notion of implication is concerned, again, going back to things you learned about bits. When they were Boolean formulae, implication was kind of B or not A, right? Those are the two ways to establish an implication. You either say what comes out is true or what goes in is false. And with bits, you can tell which of those two is the reason why the implication holds. Here you can't. This is not equivalent to B or not A.
Give the game away later on. So we need to prove this. It implies 0 equals 0, bottom. And if we squint hard enough, or if we normalize, we can see that this is, again, just double negation, right? If 0 implies 0, no, if 0 equals 0 implies the empty type, then it's just absurd. Like, it's never going to happen. And so we can use DNI on, Ruffle.
Yeah.
Right, so in a sense, we're almost doing that already.
Yeah.
But in general, so when you want to say that A does not imply B, one thing you could state is not implies AB, and that's a valid proof, right? But as we discussed earlier, it's not giving you any data whatsoever, right? You know that if at some point you get both an, if you get your hands on a B somehow, then you can break this, I think, yes? Yes? Or if you get your hands on a proof that A implies B, then you can just call this out.
Yeah.
But you could have a more constructive formulation of what it means to have a proof that it's not the case that A implies B. For instance, you could say that you know how to call any such function, so you have a proof of A, but then you also have a proof of not B. So instead of just taking the negation of the overall type, you would slowly explain what it means to have the negation of a given type. Let's see. So I would say not implies. Oh no, but I cannot actually define it. That's the whole. Go away. So we need to somehow say not implies is the same as A and not B. Not implies AB.
But you haven't got and yet.
Yeah, that's the.
We've got 3 minutes of science left.
Yeah, so that's the cliffhanger. So the idea is to then define what and means.
Right. So when I was small, my father wanted me to grow up to be annoying. So if I asked him a question like, "Are we going on Saturday or Sunday?" he would reply yes or no. If we were going somewhere at the weekend and I said, "Are we going on Saturday or Sunday?" he'd say yes. I can't resist doing the same thing, especially if both options are true. But the point is that in this world, when you see or, you're being promised one bit of information, namely, which of the two? So innocent-looking things from a kind of classical mathematical point of view, or innocent-looking things from the point of view of signals that are either 0 volts or 5 volts. The law of the excluded middle, right? Everything's true or false, right? In this world, that means I can tell the true things from the false things. It's a much stronger statement. It's not just that they have to be true or false, I just don't know which. If you're going to assert this is true or false, you have to know which. And there's no way in general. The logic is too powerful. It can express things that you can't possibly hope to know. So it's just as well the law of the excluded middle doesn't work here because it's too much magic.
I think that's a good stopping point. Yeah.